Okay, so we'll talk about energy. Energy is the most central concept that underlies all of science. Surprisingly, the idea of energy was unknown to Isaac Newton, and its existence was still being debated in the 1850s. So, I guess a little under 200 years ago, they were still debating whether energy existed. The concept of energy is relatively new, and today we find it ingrained not only in all branches of science, but also in nearly every aspect of human society. Now, don't read on. So I had to ask you right now, if I said to you, what is energy, what would you say? How would you define energy? Bea has an answer.
Movement of electrons.
Movement of electrons. Does there have to be movement? I'm not criticizing. I'm just sort of, well, I'm trying to expand that. Think about kinetic energy. What is kinetic energy?
Stored energy.
Kinetic energy is stored energy.
Yes.
Isn't kinetic energy of motion?
Yes.
Right. So something has to be moving. I think you got backwards now. Something has to be moving for there to be kinetic energy, right? Like say a volleyball flying through the air has kinetic energy. What about like a jerry can full of gas sitting in your garage there waiting to be poured into your snowblower? Does it have energy? What kind of energy? Chemical potential energy, right? The ability to do something. That's really pretty much what it is. It sounds kind of like a wishy-washy kind of, it doesn't sound very scientific, does it? And no offense intended, but that is really what energy is, the ability to do something. And whether it's already in the process of doing something or just sitting there waiting to do it, like a jerry can of gas, or for that matter, oil in the ground, right? Okay, we are all quite familiar with it. Energy comes to us from the sun in the form of sunlight. It is in the food we eat. It sustains life. Energy may be the most familiar concept in science, but it is one of the most difficult to define, and Bea did a fine job. Persons, places, and things have energy. We all have energy, some less than others, some more than others. We observe energy only when something is happening, only when energy is being transformed. And I'm going to try to highlight that, but I can't because I don't know where the highlighter thing went. I forgot to hit record, didn't I? So anyways, in the States and in Canada too, I guess, they rate engines in horsepower and electricity in kilowatts, but either can be used. In the metric system of units, automobiles are rated in kilowatts. 1 horsepower is the same as about 0.75 kilowatts. So an engine rated at 135 horsepower is a 100 kilowatt engine. I think it's about 750 watts per horsepower is what it is. Something like that. Carter, did you find anything?
No.
Okay. Maybe listen to me then. Okay, so here I got a picture of the space shuttle. The 3 main engines of a space shuttle, which are now discontinued, can develop or use 33,000 megawatts of power when fuel is burned at the enormous rate of 3,400 kilograms per second. How big do you think 3,400 kilograms of fuel is? Probably somewhere around the size of this room. Is the door locked? Okay, so imagine an average-sized swimming pool emptying in 20 seconds. That's how fast they burn fuel in the space shuttle. That's why they get so much power out of it, because they're burning it really, really fast. Mechanical energy. When work is done by an archer in drawing a bow, and I don't mean like with a pencil, this kind of drawing a bow, the bent bow has the ability of being able to do work on the arrow. When work is done to raise the heavy ram of a pile driver, the ram acquires the property of being able to do work on an object beneath it when it falls. If I raise the coffee cup up, it has stored energy, because if I drop it, and Dan sticks his finger underneath, it's going to hurt. It's going to do work. It's not going to drop my coffee cup. When work is done to wind the spring mechanism, the spring acquires the ability to do work on various gears to run a clock, ring a bell, or sound an alarm. You guys probably don't have any idea what watches that you have to wind. Maybe Grandpa's got one. In each case, something has been acquired. This something, which is given to the object, enables the object to do work. This something may be a compression of atoms in the material of an object, can be a physical separation of attracting bodies, can be a rearrangement of electric charges in the molecules of a substance. This, air quotes, something that enables an object to do work is called energy. Bea, what did you say about 15 minutes ago? Pretty much what you said. You paraphrased a little bit, but pretty much you nailed it. The ability to do work is called energy. Like work, energy is measured in joules. It appears in many forms, which will be discussed in the following chapters. For now, we're going to focus on mechanical energy, the energy due to the position or the movement of something. Mechanical energy may be in the form of either potential or kinetic energy. If I go back to the box of Kraft Dinner, that is rated at 240 calories, that is energy that is stored in here. And when you eat it, it provides you with the ability to do work, to lift coffee cups or what have you. And what happens if you don't do that work? What happens to that energy? It's stored right here. It's pretty simple. Potential energy. Holy moly, there's a lot of reading today. Hannah, you still with me? Yeah? You need the coffee cup full? Yeah? Okay. An object may store energy by virtue of its position. The energy that is stored and held in readiness is called potential energy, or PE, potential energy, because in the stored state it has the potential for doing work. A stretched or compressed spring, for example, has the potential for doing work. When the bow is drawn, energy is stored in the bow. A stretched rubber band has potential energy because of its position, or it's part of a slingshot, it's capable of doing work. The chemical energy in fuels is potential energy, for it is actually energy of position when looked at from a microscopic point of view. It's got to do with the electrons going into the higher shells. This energy is available when the position of electric charges within and between molecules are altered. That is when a chemical change takes place. Exothermic reaction. Any substance that can do work through chemical action possesses potential energy. Potential energy is found in fossil fuels like oil, electric batteries, and the food that we eat. Where does all this energy come from originally? The sun. It all comes from the sun. The sun has provided the earth with 240 calories of energy, and it has been stored in Kraft Dinner. Thanks, sun. Work is required to elevate objects against Earth's gravity. The potential energy due to elevated positions is called gravitational potential energy. Water in an elevated reservoir and the ram of pile driver have gravitational potential energy. I should keep the box of Kraft Dinner just for purposes of display in this unit. The amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity in lifting it. The work done equals the force required to move it upwards times the vertical distance it is moved. The upward force required is equal to the weight mg of the object. So the work done lifting it through at height h is given by the product mgh. Blah, blah, blah. And there I have, I've actually derived the formula for potential energy. mgh. Now I used to use mgd for distance, but it caused people to giggle. Because for some reason, naming a type of beer in high school causes people to giggle. So now I don't do it. mgh. But you might see mgd on occasion. Note that the height h is the distance above some reference level, such as the ground or the floor of a building. The potential energy mgh is relative to that level and depends only on mg and the h. In other words, the amount of energy that's in the coffee cup right now is relative to the floor, because if I go like this, it's going to smash, right? And if I do this, right, it's going to smash here. What if I put it on the floor? Does it have any potential energy?
No.
It does. We're here on the second floor, are we not? So it's all relative. It's kind of like Christmas dinner.
Where is it going to fall?
Yeah. You like that one, Joel? It's all relative?
I laugh for you.
For my... Thanks, man. I think you're mocking me. Okay. So, little summary here at the end. I know you guys have been doing awesome. Thanks for hanging in there. The potential energy of the 100 Newton boulder with respect to the ground below is the same. It's 200 joules. In each case, because the work done in elevating it 2 meters is the same whether it was lifted with 100 newtons of force. So here, the rock is 2 meters high. It has 200 joules of energy. What if you roll it up a 4 meter long ramp? It's still 2 meters high, so it has a certain amount of potential energy, 200 joules. What if you carried it upstairs? Still has 200 joules. Which one is easier? The ramp. Does it have the same amount of energy? Yep. Do you burn the same amount of calories doing it? You do, actually. Right? Because you've taken 200 joules of Kraft Dinner and stored it in the rock. Right? Now, it might, okay, well then you get into that, whole, you're holding it there, you're not doing work. Are you burning calories?
You're doing work on biological.
You're doing work on a biological. Yeah, so we do have to sort of clarify a little bit. But I mean, I'm obviously simplifying it considerably. Okay, so how much work is done on a 100 Newton boulder that you carry horizontally across a 10-meter room? So I don't have a boulder, so I'm going to use a laptop. Okay, standing here, holding my 100 Newton laptop. Am I doing any work?
No.
No work, just standing here. Walking over here. Did I do any work? No, did not. I know, it's confusing. How much energy does it have here? 100, whatever, has 100 joules, some number. Has 100 joules right here because it's a certain height off the floor. And I carry it over here. How much energy does it have here? The same amount. Have I taken away any energy? Have I added any? No. I have done no work. You guys are familiar with that, right?
Potential energy is only up and down.
Oh, what does that mean?
How many? Potential energy is only up and down. Right? Now, if it was heavier, would I be burning calories carrying across like this? Yeah, that's not, you got to get that out of your head. Just because it's hard or you have to apply a force doesn't mean you're doing work. The force and the direction have to be in the same, I'm same direction. I'm forcing it up, but I'm moving it.
You're saying you're storing no calories inside that laptop.
Right. I'm not taking any energy, no Cheerios that I had for breakfast are being transformed into potential energy.
So in what way? Back?
Woo! There goes all those Cheerios.
What happens when you let it fall down slowly?
What's the difference between
Like that?
Does that give you energy?
No.
Where does that energy go?
Oh, there's the question. Where does that energy go? Awesome. I've been waiting for someone to say that. Where does the energy go? It doesn't have to go into gravitational potential because I actually, just me working on it, I've actually worked up a little bit of a sweat. Right? I'm not, I didn't really work up a sweat. But when you're working out on that elliptical, right, you not only burn energy, but you also create heat, right? You create heat. That's why you need to eat to stay warm, too, right? Because some of your Kraft Dinner, your Cheerios, just goes towards keeping your body warm. So it's not just work that burns energy, which is why working out early in the morning or doing it at a high rate increases your metabolism because your body's warm for a longer period of time, right? So you're burning energy then too.
Okay. What's the difference between lifting something up and then letting it drop down slower? Is that like taking away its potential energy?
Yeah, you're right. You're taking it away. You are still applying a force, right? So that work is done on that biological scale on your muscles, and the energy is dissipated as heat. Yeah, but you're not technically, when you lower something, you're not technically doing any work because it's not in the same direction.
But you're still changing it.
Yeah, you are.
We only lift.
I know, it's circular, right? Well, this is just the intro. Don't worry. How much work is done on a 1 Newton boulder when you lift it 1 meter? 100 newtons times 1 meter, it would be 1,000 joules. What power is expended if you lift it in 1 second? It would be 1,000 divided by 1. It would be 1,000 watts. Blah, blah, blah. I should just get rid of those questions. These are so easy, you guys. You're going to just love these. So, work done against friction. How much work is done when a sliding 30-kilogram chair, at a distance of 50 meters across a rough surface where the force of friction is 50 newtons? Okay, so, right? Friction is 50 newtons. So that means then that the applied force would have to be, if it's a constant speed, does it say constant speed? It doesn't, right? So the applied force would have to be 50 newtons, right? The applied force, the friction force would have to be the same. Work equals FD. Seriously, it's this easy. 50 times 15.
So where does the 30 come in?
Doesn't.
Or why is it?
Because I'm showing you the mass doesn't matter. Right? Am I right with my numbers? 750 joules? So Hannah asked, what's the deal with the 30 then? Well, the 30 kilograms, you know that whole mu equals FF over Fn, right? So the bigger the mass, then the greater the friction force, right? The bigger the Fn. So we're going to get to that. This is obviously the very simple one right at the start here.
Why not say that it doesn't matter?
Well, in this case it doesn't matter because I've given you the friction force.
Okay, cool. All good.
Okay, what about work done against gravity? How much work is done in lifting 2 bricks, each a mass of 1.4 kilograms from the floor to the top of your table, a distance of 80 centimeters? And yes, I put it in centimeters for a reason. Right? So what is the force? How much force do you need? It's going to be mass times gravity. There's 2 bricks, each 1.4. So 2 times 1.4, right, times 9.8. I didn't actually write that number down. I did it all at once, but I'm going to do it this way this year. 27.44? 27.44. That's in newtons. That's the force that you need. And then work equals FD. But the D must be in meters. The displacement must be in meters. So it's going to be 27.44 times 0.8. That's a poorly drawn 8. I get 21.9. 21.95, I guess. And that would be joules. Are these easy? Yeah. Yeah. If I started out with the hard, I would. Did I go too fast? Okay, this time we got a dynamics cart, one of those little crash thingies. Oh, by the way, Monday we'll be back in the other room. They're pretty much done. I just got to put some stuff away, so I'm going to come in Saturday to do that. The 1.5 kilogram dynamics cart is pulled at an angle of 30 degrees above the horizontal with a force of 25 newtons. The cart moves 4 meters. How much work was done on the cart? Does it matter that it's at an angle? Ah, you are. But which direction is the work count? Up and down or left and right? Actually, it is both, really, because are you actually lifting it or are you just sort of reducing friction? Probably just reducing friction. So the work is actually only sideways. So what force do I use? Do I use 25? I have to do what? I have to find that. I use this notation with you guys, right? FAX? Okay, good. So FAX is going to be FA cos theta. So it's 25 cos 30. So that's how much force is just sideways. Someone's excited. And now we're going to go. Work equals FD, 21.7, 4 meters, 86.6. These are easy. Good thing we talked about ramps earlier. Now, do you have a picture there?
Yeah.
You have a picture, but I don't. That seems wrong. Okay. Oh. Okay, so how much work to pull the cart up the plane? Hang in here, guys. We got an FD. It doesn't say anything about friction, so the applied force up the ramp has to be equal to the FD down the plane, which we all remember from that one unit. See how it all ties together? FD is equal to mg sine theta. Remember that, friend, from before? What are you talking about? It's all going to be everything. Like we just keep reviewing. It's not like 8 completely separate units. It's really just one big long unit that we've been building to. I will say this though. This is the first year that I've truly realized, I don't know why, but I've truly thought about how I keep coming back to things. And like when we did that vector subtraction there the other day, I never considered that before. Literally, it's just coming back. The same things over and over again, right? Slightly different situations, but it's the same concepts. It really is. And so maybe if I can get you to realize that, maybe people say, oh, physics exam's easy. Would you do that for me?
If you give me a name, what you're in the exemption.
mg sine theta. So it's going to be 30 times 9.8 times sine 30. So the FD down the plane is 147 newtons. But how much work is done? So that's going to be 147. Now, which D do I use? The 6 or the 3? I use the 6 because that's the distance that I have to apply this 147 newtons. I have to apply 147 newtons for 6 meters. So I end up doing 882 joules of work.
Would there ever be a time where you would have to use the 3?
We're going to do it in part B. The amount of work done lifting the cart straight up. Part B says, what if instead of using the ramp, I'm just going to lift it? Is it going to need more force to lift it? Yeah. How much force? Well, the weight force, m times g. So it's going to be 30 times 9.8, which is having a hard time here. 294. Is it more force required? Yeah, look at 294 newtons compared to 147 newtons. Way harder. But I only have to do it over 3 meters. What do you think the work done is going to be? I know the answer. I'm just doing this for dramatic effect. It's 882 joules. Exactly the same. How come? Because it's in exactly the same spot whether you lifted it or whether you rolled it up the ramp, right? So it has the same amount of potential energy. So you could either work really hard for a shorter distance, or you could have things a little bit easier. You just got to do it longer. In fact, ramps are considered one of the basic simple machines, right? And the longer the ramp, the easier it is to push. You just have to do it longer. It's a trade-off. It's that whole balance kind of thing. It's like, like negotiations. I'll make it easier for you. You just got to do it longer. Now, what if there's friction? Come on, what if there's friction? And there always is, right? If there's friction, then we got another force. So now my applied force is going to have to be 147. How much friction was it? 50. So I have to do 50 extra newtons of force. I now have to push with 197 newtons. work done equals FD. Now it's going to be 197 times that 6. And you get 1182 joules. Whoa, how can you have more potential energy? You can't. You have the same amount of potential energy. So ask the question again, Dan. Where does the energy go? Heat. When you push something up a ramp, it's going to generate some heat, right? Why do your hands get warm when you rub them together? Friction.
So we do 1182 minus 882, and that's.
That would be the amount of actual heat that's generated. Absolutely. We had ovens in science a long time ago. You could actually take food, throw it in an oven, and then measure the difference in heat given off, and that's how they actually figure out how much food energy is in it, because it's how much little heat is generated. They know how much heat they're putting in, and what, pardon me? 300?
What's
In fact, it would be, Shelby, it would be the 50 newtons times the 6 meters, right? 50 times 6 would be 300, wouldn't it? There you go. Probably time for me to be quiet now, eh? You guys have been listening to me a long time. Okay, I would suggest, give me a second, Dan. You've got 2 packages there. I'm going to do this one tomorrow. I'll talk about this work one tomorrow. You'll be fine with it. You've got 2 packages. There's this one here. I spent a little time the other day putting QR codes on for you, because they didn't have them. So there's that one there, and there's this one here. This is more than enough to get you started. I'll do a few more sort of samples and ropes and thoughts tomorrow, and then we'll have the weekend, and then we're going to jump right into kinetic energy, potential energy, spring energy next week. So tomorrow, Shelby, I'll probably give people a little bit of time to work because you're not getting this time today. I will go through this here, and I think it's set of notes. What time? You're leaving right away, right?